Hello friends, now today we will do chapter 2 of Zone, the first chapter, introduction to stress strain, we have done in lecture 1. Now let's start the chapter 2. Now we have chapter 2, that is axial loading. Axial loading. So first point, very simple, like if I consider a rod and I apply a force here, then basically I want to calculate here support reactions here, and then we will calculate in the second part force deformation diagram. This will be used to calculate the third part, that is deformation, and deformation is very easy, area upon AE, axial rigidity. Axial rigidity, AE is the property of the material, right? And after that we will calculate strain energy per unit volume. It will be P square L upon AE, and square, then we will apply a 2 also. So this is strain energy per unit volume, right? Like if I want to solve this thing, then what I'll do, support reaction, there is a force in this direction, so I'll get a support reaction here, only F, right? And now I'll draw F delta representation. So this force is in this direction. Let us consider this is positive direction, so this is F, and then there is no other force which is perpendicular to the cross section, it will be same, and at this point the force is in this direction, and if I'm taking this positive, this side will be negative, so here I'll go down F, and finally this is our diagram. And then simply I want to calculate the deformation. So deformation is what? The area of this part. Let us consider the length of this rod is L. So what is the area? L into F means FL upon AE is universal. So this is the deformation in this rod. And last I want to calculate strain energy. So strain energy is what? Load, that is F square L upon 2A E. So this is strain energy in this rod when a force is applied on it, right? Now the second point is, as we know, epsilon T, that is thermal strain. Thermal strain only depends on change in temperature, and if proportionality is removed, thermal strain is alpha delta T, and change in length due to temperature will be delta L by L, and L goes this side, so deformation due to thermal strain is alpha delta T L. So this is deformation due to temperature, right? Now here we are getting some cases, like the first case, if the rod is fixed at both the ends, and if I increase the temperature, what happens? The rod want to expand this much, but it will not due to support, right? And here you can apply a very short trick, like if I calculate delta L, change in length, let us assume this is not present. If this is not present, then what will be the deformation? It will be alpha delta T into L, right? And just equate it by this. Delta L is what? Force PL upon AE, and P upon A will be what? Thermal stress. So finally I am getting delta L is equal to thermal stress L by E, and from here I can calculate thermal stress as thermal stress which is developed in this rod is delta L E by L. So this is thermal stress in the body. Now another case, if the rod is free, means no other support reaction is here, then simply it can expand freely, so no stress is generated, so thermal stress will be 0 in this condition, right? And the third case is if the rod is allowed to deform by X, right? So simply what you will do, deformation, the total deformation minus X, minus XY, because this expansion can be present. No stress is generated for X, so that's why the length in which the stress is not generated is subtracted. So delta L minus X, delta L is what? Delta L is this much whole part, but I want only this part, because this will be having a thermal stress, right? So that's why delta L minus X, this is the deformation, it will be what? Alpha delta T L. And now what you will do, this, let us consider it is thermal deformation. So thermal deformation is what? The formula thermal deformation is P PL upon AE, PL upon AE, and this P upon A is sigma. So sigma TH, thermal stress, L upon E, right? So therefore you can assume it delta L minus X is what? Sigma TH, L by E. So from here you can calculate thermal stress in this body. Clear? Now let us move further. And remember one more thing, like this body, due to temperature rise, this body wants to go in this direction, but this support will apply a compressive stress. So this stress which is coming, this will be compressive in nature. Now let us move further. So this was all about strain, stress and strain due to temperature. Now next, third part. Now I'll calculate stress and strain on oblique plane, right? Oblique plane means if I'm considering a body, and let us consider an oblique plane. This is an oblique plane, and from this direction I'm taking anti-clockwise theta, and here the body is having sigma x, sigma y, and tau xy, and this is in anti-clockwise direction. Then I'll take here a clockwise direction, tau ix, right? So this will be positive for us. This is the sign convention. Sigma x positive if it is in this direction, sigma y positive in this direction, and tau xy positive in this anti-clockwise direction, and theta is positive for anti-clockwise direction, right? So if I want to write the stress on this plane, normal stress is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 sin 2 theta. Sorry, first cos will come, cos 2 theta plus tau xy sin 2 theta. So this is normal stress at this plane. Similarly, shear stress will be what? Just differentiated. So cos differentiation is minus. So minus sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. So this is shear stress on this plane, right? So that is the cases. Now if you want to calculate the deformation energy, strain energy, then you can use the formula, these formulas. Now on this, let us do one question. Like for example, like if I have a rod which is fixed at both the ends, and the property of the material is A1 E1, A2 E2, L1 L2, right? So first of all we will calculate the support reactions. So here you can see, and one more thing, a force F is acted here, right? So for support reactions, what I'll do, I'll apply, just a minute, I'll apply a reaction here. Let us consider reaction in this direction, RBX, RAX, this is point A, this is point B, right? So simply what I'm getting, RAX plus RBX is equal to F, right? So if I'm going to draw its force deformation graph, what I'll get, this is in this direction, this is positive RAX, and no force is applied, so the sign is same, and this F is what? The sum of these two forces now. So it will be very large, then the line will cross the x-axis, right? And here I have positive RBX, so I'll go here and I'll do a positive RBX. This is RBX, right? So this is positive and this is negative. Now if I want to calculate the deformation in AB, it will be what? Simple, the area of this part upon AE, area of this part upon AE. So area is RAX L 1 upon A1 E1, and here we will have a negative. So minus, what will be the reaction? I can write F minus RAX into L2 upon A2 E2 is equal to, the deformation is 0 because they are fixed at both the ends. So deformation is equal to 0. From here you can calculate RAX, right? So this is equation 1, this is equation 2. By solving these two equations, you will get RAX and RBX, right? So if you want to write directly, you can write it like RAX is equal to RAX, and this force is present, so F, and if I am calculating RAX, I'll write L2, FL2 upon total length L. Similarly, if I want to write RBX, it will be what? It will be F, the opposite length, L1 upon L. So these two reactions are calculated, right? If I know the reaction, I can write strain energy equation as well. So strain energy is what? The load square. Now load is on this part, load is Rax square into L1 upon 2 A1 E1, and here it will be now the load plus load square. So load is minus RBX square L2 upon 2 A2 E2. So this is the strain energy equation, right? So similarly you can solve all the questions. So chapter 2 is done. Now let us see chapter 3. The third chapter is torsion. Torsion, right? So first of all, torsion means what? If I take a bar and if I apply a torque here, T, and due to this torque, the cross section, if I talk about the cross section gets twisted, right? So for example, if I draw something like this in 3D, if I'm considering a point here, this will go to this point, due to which it will sustain some angle theta here. Getting? So this is called twist. This is twist, right? So the equation, the governing equation is due to twist, T by J is equal to G theta by L is equal to tau by R. Now this is very important. Earlierly, on earlier basis, we have done the axis. This is standard x-axis, standard y-axis, and standard z-axis, right? So if I am taking the twist along z, right? So if T twist is along, you can say along x-axis or in yz plane, along x-axis, then J is called polar moment of inertia, and it will be also along x, right? For circular shaft, the moment of inertia is given by pi d4 by 64, and polar moment of inertia J is pi d4 by 32, right? And from here we can do two things. I can equate this by this. You can get tau, shear stress. So T by J is equal to tau by R. From here the tau comes T by J into R, and tau max will be 16 T by pi d cube. Right? And from here one more thing comes, that is, okay, now if I this is tau max by equating these two things. Now you can equate these two things. So B T by J is equal to G theta by L. And what is G theta? G theta is called not G theta, GJ, right? GJ. From here you can calculate the angle of twist. Theta is equal to TL upon GJ, right? And this GJ is called torsional rigidity. This is called torsional rigidity, GJ. Clear? And similarly, now one more thing is there, like if the torque is divided by the angle of twist, this is called torsional stiffness. Like force per unit deformation is K, and this is called axial stiffness. Like spring, F is equal to Kx. K is what? It is also a stiffness. It is spring stiffness. Right? So these are the things which is important. Torsional stiffness, and this is axial stiffness. Axial loaded members is having axial stiffness, right? And spring is having spring stiffness. It is clear? Now, second, if I talk about a circular shaft, the maximum shear stress will be at the top fiber, and at the central fiber the shear stress will be 0, and it will be again maximum at the lowermost point. So this is the stress representation in a circular shaft, right? Now if this is tau max, right? This is only tau max. Now third, if shafts in it can happen in two parts, series or it can be in parallel. Series means like this. So this is in series. So in series, what happened? The torque remains same. And in parallel, like this, torque is same here. Then here theta will be same. Or constant, anything you can say. Right? And if I talk about hollow shaft. Hollow shaft. In hollow shaft, what happens? If you want to calculate polar moment of inertia, it is very easy. Pi by 32 d outer 4 minus d inner 4. Just I have done a subtraction. So this is polar moment of inertia of hollow shaft. And one more thing, like here I have written torsional stiffness. The torsional stiffness could also be written as what? T by theta. From here you can calculate T by theta, T, and theta comes down, Gj by L. This is Gj by L. Right? And we know already what is Gj? It is torsional stiffness. Sorry, what is Gj? Torsional rigidity. This is torsional rigidity. Right? And similarly, here also, force per unit deflection. And similarly here also, if you will substitute the value of deformation. What is deformation? PL or FL upon AE. Then you will get axial rigidity as F, and F got cancelled out. So AE by L. Right? AE by L. GJ. AE is axial rigidity. Sorry. Axial rigidity. Okay, so that was the point. Now let us move forward. Now one more important thing, that is the fifth point. Now we will compare solid and hollow shaft. Compare solid and hollow shaft. Right, I'm not going to derive the things. Just we will calculate, we'll write the expressions. Like shear stress, maximum shear stress for hollow is what? It is solid into 1 upon 1 minus K4. Right, this is very important. And what is K? K is inner dia upon outer dia. Right, inner dia upon outer dia. So this will be less than 1 because the inner dia will be less. Right. So that is important. The factor which comes here, 1 upon 1 minus K4. Similarly, if I want to write polar section modulus, polar moment of inertia. Section modulus will come in next chapter. Polar moment of inertia, max, hollow, is what? J solid. And the factor which comes here, बस ये चीज़ को हमें multiply में लिखना होगा. 1 minus K4. This is in multiplication. There it was in division, and here it is in multiplication. So J solid, 1 minus K4. And in the similar way, J, we are getting W, weight. Weight max hollow is what? Solid, 1 minus K4. So J and W formula is same. Tau is inversely proportional, right? But remember one important point, that these all comparisons are done for same torque, torsion, and restricted outer dimension. Right? Otherwise the formula will be changed if this condition is not valid. So that's all from chapter 3rd. Right? And more you can do the practice of questions. Thank you.